Ring theory is the branch of mathematics in which rings are studied, that is, structures supporting both an addition and a multiplication operation. This is a glossary of some terms of the subject. Definition of a ring. A ring is a set R with two binary operations, usually called addition and multiplication, such that R is an abelian group under addition, R is a monoid under multiplication, and multiplication is both left and right distributive over addition. Rings are assumed to have multiplicative identities unless otherwise noted. The additive identity is denoted by 0 and the multiplicative identity by 1. Subring A subset S of the ring, which remains a ring when plus and times are restricted to S and contains the multiplicative identity 1 of R, is called the subring of R. Types of elements. Associate in a commutative ring, an element A is called an associate of an element B if A divides B and B divides A. Central in element R of a ring R is central if XR equals Rx for all X in R. The set of all central elements forms a subring of R, known as the center of R. Divisor in an integral domain R, an element A is called a divisor of the element B if there exists an element X in R with X equals B. Idempotent an element R of a ring is idempotent if R2 equals R. Integral element for a commutative ring B containing a subring A. An element B is integral over A if it satisfies a monic polynomial with coefficients from A. Irreducible an element X of an integral domain is irreducible if it is not a unit and for any elements A and B such that X equals AB. Either A or B is a unit. Note that every prime element is irreducible, but not necessarily vice versa. Prime element. An element X of an integral domain is a prime element if it is not 0 and not a unit and whenever X divides a product AB. X divides A or X divides B. Nilpotent. An element R of R is nilpotent if there exists a positive integer n such that Rn equals 0. Unit or invertible element. An element R of the ring R is a unit if there exists an element R-1 such that R-1 equals R-1 R equals 1. This element R-1 is uniquely determined by R and is called the multiplicative inverse of R. The set of units forms a group under multiplication. Von Neumann regular element. An element R of a ring R is von Neumann regular if there exists an element X of R such that R equals Rxr. Zero divisor. An element R of R is a left zero divisor if there exists a non-zero element X in R such that Rx equals 0 and a right zero divisor, or if there exists a non-zero element Y in R such that Y equals 0. An element R of R is called a two-sided zero divisor if it is both a left zero divisor or a right zero divisor. Homomorphisms and ideals. Finitely generated ideal. A left ideal I is finitely generated if there exist finitely many elements A1, and such that I equals Ra1 plus Ran. A right ideal I is finitely generated if there exist finitely many elements A1, and such that I equals A1R plus ANR. A two-sided ideal I is finitely generated if there exist finitely many elements A1, and such that I equals Ra1R plus RANR. Ideal A left ideal I of R is a subgroup of R such that I for all are R. A right ideal is a subgroup of R such that I or I for all are R. An ideal is a subgroup which is both a left ideal and a right ideal. Jacobson radical. The intersection of all maximal left ideals in a ring forms a two-sided ideal. The Jacobson radical of the ring. Kernel of a ring homomorphism. The kernel of a ring homomorphism F. Rs is the set of all elements X of R such that F equals 0. Every ideal is the kernel of a ring homomorphism and vice versa. Maximal ideal. A left ideal M of the ring R is a maximal left ideal if M R and the only left ideals containing M are R and M itself. Maximal right ideals are defined similarly. In commutative rings, there is no difference, and one speaks simply of maximal ideals. Nil ideal. An ideal is nil if it consists only of nilpotent elements. Nilpotent ideal. An ideal I is nilpotent if the power ik is 0 for some positive integer k. Every nilpotent ideal is nil, but the converse is not true in general. Nil radical. The set of all nilpotent elements in a commutative ring forms an ideal, the nil radical of the ring. The nil radical is equal to the intersection of all the ring's prime ideals. It is contained in, but in general not equal to, the ring's Jacobson radical. Prime ideal. An ideal P in a commutative ring R is prime if P R and if for all R and B in R with AB in P, we have R in P or B in P. Every maximal ideal in a commutative ring is prime. There is also a definition of prime ideal for non-commutative rings. Principal ideal. A principal left ideal in a ring R is a left ideal of the form R for some element R of R. A principal right ideal is a right ideal of the form R for some element R of R. A principal ideal is a two-sided ideal of the form R for some element R of R. Quotient ring or factor ring. Given a ring R and an ideal I of R, the quotient ring is the ring formed by the set R, I of cosets, A plus I, R together with the operations plus equals plus I and equals AB plus I. The relationship between ideals, homomorphisms, and factor rings is summed up in the fundamental theorem on homomorphisms. Radical of an ideal. The radical of an ideal I in a commutative ring consists of all those ring elements a power of which lies in I. It is equal to the intersection of all prime ideals containing I. Ring homomorphism. A function f Rs between rings and is a ring homomorphism if it satisfies f equals f, f equals f times f equals 1 for all elements R and B of R. Ring monomorphism. A ring homomorphism that is injective is a ring monomorphism. Ring isomorphism. A ring homomorphism that is bijective is a ring isomorphism. The inverse of a ring isomorphism is also a ring isomorphism. Two rings are isomorphic if there exists a ring isomorphism between them. Isomorphic rings can be thought as essentially the same, only with different labels on the individual elements. Trivial ideal. Every non-zero ring R is guaranteed to have two ideals, the zero ideal and the entire ring R. These ideals are usually referred to as trivial ideals. Right ideals, left ideals, and two-sided ideals other than these are called non-trivial. Types of rings. Abelian ring. A ring in which all idempotent elements are central is called an abelian ring. Such rings need not be commutative. Artinian ring. A ring satisfying the descending chain condition for left ideals is left Artinian, if it satisfies the descending chain condition for right ideals. It is right Artinian. If it is both left and right Artinian, it is called Artinian. Artinian rings are noetherian. Boolean ring. A ring in which every element is multiplicatively idempotent is a Boolean ring. Commutative ring. A ring R is commutative if the multiplication is commutative, i.e., Rs equals R for all R, SR. Dedekind domain. A Dedekind domain is an integral domain in which every ideal has a unique factorization into prime ideals. Division ring or skew field. A ring in which every non-zero element is a unit and one zero is a division ring. Domain. A domain is a non-zero ring with no zero divisors except 0. This is the non-commutative generalization of integral domain. Euclidean domain. A Euclidean domain is an integral domain in which a degree function is defined so that division with remainder can be carried out. It is so named because the Euclidean algorithm is a well-defined algorithm in these rings. All Euclidean domains are principal ideal domains. Field. A field is a commutative division ring. Every finite division ring is a field, as is every finite integral domain. Finitely generated ring. A ring that is finitely generated as Z algebra. Finitely presented algebra. If R is a commutative ring and A is an R algebra, then A is a finitely presented R algebra if it is a quotient of a polynomial ring over R in finitely many variables by a finitely generated ideal. Hereditary ring. A ring is left hereditary if its left ideals are all projective modules. Right hereditary rings are defined analogously. Integral domain or entire ring. A non-zero commutative ring with no zero divisors except 0. Invariant basis number. A ring R has invariant basis number if room isomorphic to Rn as R modules implies M equals N. Local ring. A ring with a unique maximal left ideal is a local ring. These rings also have a unique maximal right ideal, and the left and the right unique maximal ideals coincide. Certain commutative rings can be embedded in local rings via localization at a prime ideal. Noetherian ring. A ring satisfying the ascending chain condition for left ideals is left noetherian. A ring satisfying the ascending chain condition for right ideals is right noetherian. A ring that is both left and right noetherian is noetherian. A ring is left noetherian if and only if all its left ideals are finitely generated, analogously for right noetherian rings. Null ring. CRNG of square 0. Perfect ring. A left perfect ring is one satisfying the descending chain condition on right principal ideals. They are also characterized as rings whose flat left modules are all projective modules. Right perfect rings are defined analogously. Artinian rings are perfect. Prime ring. A non-zero ring R is called the prime ring if for any two elements A and B of R with R B equals 0, we have either A equals 0 or B equals 0. This is equivalent to saying that the zero ideal is a prime ideal. Every simple ring in every domain is a prime ring. Primitive ring. A left primitive ring is a ring that has a faithful simple left R module. Every simple ring is primitive. Primitive rings are prime. Principal ideal domain. An integral domain in which every ideal is principal is a principal ideal domain. All principal ideal domains are unique factorization domains. Quasi-Frobenius ring. A special type of Artinian ring which is also a self-injective ring on both sides. Every semi-simple ring is quasi-Frobenius. Rng of square 0. A Rng in which x, y equals 0 for all x and y. These are sometimes also called zero rings, even though they usually do not have a 1. Self-injective ring. A ring R is left self-injective if the module RR is an injective module. While rings with unity are always projective as modules, they are not always injective as modules. Semi-primitive ring or Jacobson semi-simple ring. This is a ring whose Jacobson radical is 0. Von Neumann regular rings and primitive rings are semi-primitive, however quasi-Frobenius rings and local rings are usually not semi-primitive. Semi-simple ring. A semi-simple ring is a ring R that has a nice decomposition, in the sense that R is a semi-simple left R module. Every semi-simple ring is also Artinian, and has no nilpotent ideals. The Artin-Wedderburn theorem asserts that every semi-simple ring is a finite product of full matrix rings over division rings. Simple ring. A non-zero ring which only has trivial two-sided ideals is a simple ring. Trivial ring. The ring consisting of a single element 0 equals 1, also called the zero ring. Unique factorization domain or factorial ring. An integral domain R in which every non-zero non-unit element can be written as a product of prime elements of R. This essentially means that every non-zero non-unit can be written uniquely as a product of irreducible elements. Von Neumann regular ring. A ring for which each element A can be expressed as A equals AXA for another element X in the ring. Semi-simple rings are von Neumann regular. Zero ring. The ring consisting only of a single element 0 equals 1, also called the trivial ring. Sometimes, zero ring is alternatively used to mean Rng of square 0. Ring constructions. direct products of a family of rings. This is a way to construct a new ring from given rings by taking the Cartesian product of the given rings and defining the algebraic operations component-wise. Endomorphism ring. A ring formed by the endomorphisms of an algebraic structure. Usually its multiplication is taken to be function composition, while its addition is pointwise addition of the images. Localization of a ring. For commutative rings, a technique to turn a given set of elements of a ring into units. It is named localization because it can be used to make any given ring into a local ring. To localize a ring R, take a multiplicatively closed subset S containing no zero divisors, and formally define their multiplicative inverses, which shall be added into R. Localization in non-commutative rings is more complicated, and has been defined several different ways. Matrix ring. Given a ring R, it is possible to construct matrix rings whose entries come from R. Often these are the square matrix rings, but under certain conditions, infinite matrix rings are also possible. Square matrix rings arise as endomorphism rings of free modules with finite rank. Opposite ring. Given a ring R, its opposite ring ROP has the same underlying set as R. The addition operation is defined as in R, but the product of S and R in ROP is RS, while the product is senior in R. Projective line over a ring. Given a ring R, its projective line P provides the context for linear fractional transformations of R. Polynomial rings. Differential polynomial ring. Formal power series ring. Laurent polynomial ring. Monoid ring. Polynomial ring. Given R a commutative ring. The polynomial ring R x is defined to be the set with addition defined by, and with multiplication defined by, some results about properties of R and R x. If R is UFD, so is R x. If R is Noetherian, so is R x. Ring of rational functions. Skew polynomial ring. Given R a ring and an endomorphism of R, the skew polynomial ring is defined to be the set, with addition defined as usual, and multiplication defined by the relation. Miscellaneous characteristic. The characteristic of a ring is the smallest positive integer and satisfying nx equals 0 for all elements x of the ring, if such an n exists. Otherwise, the characteristic is 0. Krull dimension of a commutative ring. The maximal length of a strictly increasing chain of prime ideals in the ring. Ring-like structures. The following structures include generalizations and other algebraic objects similar to rings. Nearing a structure that is a group under addition, a semigroup under multiplication, and whose multiplication distributes on the right over addition. RNG, an algebraic structure satisfying the same properties as a ring, except that multiplication need not have an identity element. The term RNG is meant to suggest that it is a ring without an identity. Semi-ring, an algebraic structure satisfying the same properties as a ring, except that addition need only be an abelian monoid operation, rather than an abelian group operation. That is, elements in a semi-ring need not have additive inverses.